Welcome to the deep dive. Today we're digging into a technical report. It sort of pulls back the curtain on some new AI models.
That's right. These are models designed to really improve how computers understand text. Our source for this is excerpts from a report called Qwen3 Embedding, Advancing Text Embedding and Re-ranking Through Foundation Models.
And our mission today is to unpack the key insights from that report. We're focusing on the new Qwen3 embedding series models, specifically how they handle text embedding and re-ranking.
Yeah, and the report emphasizes right away, that these aren't just lab concepts. Text embedding, re-ranking, they're core parts of things we use daily. Think search engines, chatbots answering questions, recommendation systems.
Okay, so fundamental stuff for information retrieval.
It's about machines getting the meaning behind text and showing you the most relevant information.
So these models are tackling a pretty central challenge. Let's start with the basics then. What exactly is this Qwen3 embedding series, according to the report?
Well, the report says they're built directly on top of the Qwen3 large language model. So they're leveraging the power of those foundational models that are already known for strong language skills.
And they come in different sizes, I gather. The report mentioned that.
Yes, three sizes, zero point 0.6 billion, 4 billion, and 8 billion parameters. They did this for both the embedding and the re-ranking tasks.
So users can choose based on their needs.
That seems to be the idea. You can pick based on whether you need, say, more speed and efficiency, or if you're pushing for the absolute best performance.
Okay, that makes sense. Covering different deployment scenarios, how does the report describe the architecture? How do these models actually, do the embedding or re-ranking?
So the report states they use the dense version of the Qwen3 models. For the embedding model specifically, it mentions causal attention. And a key detail is how they get the final embedding vector. They add a special token, the EOS, or end-of-sentence token, to the input. The embedding itself is then taken from the hidden state of the model's final layer, right at that EOS token position.
Ah, okay. So that token's position acts like a summary point for the whole input.
Sort of, yeah. It's a common technique to condense the sequence information.
The report also mentioned something about instruction following. How does that play out differently for embedding versus re-ranking?
Right, that's an interesting feature they discuss. For embedding, it's about context. The instruction you might give, like retrieve passages about climate change, gets concatenated, just joined together with the actual query text. This whole thing goes into the model. It helps the model generate an embedding that reflects the intent behind the query.
But not for the document being embedded.
Correct. The document itself doesn't get the instruction attached, just the query does.
And re-ranking, the report suggested a different method there.
Yeah, for re-ranking, they frame it differently. It uses more of the underlying LLM's chat capability. They set it up using a chat template. The instruction, the query, and a candidate document are all put into this context, and the model's task becomes essentially a yes-no question. Is this document relevant to this query, given this instruction?
A binary classification, yes or no. That's a clever way to handle re-ranking.
The report suggests it plays well to the strengths of LLMs in classification. They also mention other practical bits, like flexible embedding dimensions. You can choose the size of the vector output, and you can customize the instructions for both model types, which is useful for tailoring them to specific needs.
Okay, so we have a picture of what they are and how they work based on the report. Now, a report spent quite a bit of time on the training process. It described a multi-stage pipeline. Could you walk us through that?
Sure. They outline this multi-stage training, which, as they note, isn't entirely uncommon.
Yeah.
They often start broad and then refine, but they highlight a few key innovations they introduced for this series.
Innovations. What did the report point to?
The first big one is something they call large-scale synthetic data-driven weak supervision training. This is where it gets quite interesting. Instead of just relying on, say, massive web scrapes, which can be noisy.
They made their own data.
In a way, yes. They use their own powerful foundation model, Qwen3 32B, to synthesize or generate training data.
Using an LLM to make data for other LLM-based models?
That's the idea. The report stresses the control this gives them. They could generate huge amounts, around 150 million pairs, it says. And they could control the type of data, the language's difficulty, all tailored for the task. Much more control than just open domain stuff.
Wow, 150 million synthetic pairs. That's a huge scale. What was the second innovation mentioned?
The second one builds on that. Because the report claims this synthetic data was high quality, they use some of it again later. In the second stage, the supervised fine-tuning stage, they mixed this high-quality synthetic data, about 12 million pairs, with more traditional labeled data sets, which was around 7 million pairs.
So synthetic data wasn't just for the initial broad training, but also for the more focused fine-tuning stage.
According to the report, yes. They suggest it helped boost performance and generalization even further.
Okay, and there was a third innovation.
Yes, model merging. After the fine-tuning, they didn't just pick one final model checkpoint. They used a technique based on something called spherical linear interpolation, or SLIRP, to merge multiple checkpoints from different points in the fine-tune.
Merging models. What's the reported goal of that?
To improve robustness and generalization, make the final model work better across different kinds of data it might encounter.
Did the re-ranking models follow this exact same path? The report mentioned a difference, I think.
Good point. The report clarifies that the re-ranking models skip that first big stage of weekly supervised pre-training with 150 million pairs. They start more directly with the supervised fine-tuning stage, using that mix of high-quality synthetic and labeled data, and then the model merging.
Okay, let me see if I have this right based on the report. For embedding models, massive synthetic data pre-training, then fine-tuning with high-quality synthetic and labeled data, then model merging. For re-ranking models, skip the first stage, go straight to fine-tuning with the mixed data, and then model merging.
That's a good summary of the process described in the report.
So the big question, how did all this translate into performance? The report included comprehensive evaluations, right?
Oh, yes, quite detailed. They tested against a whole suite of benchmarks, things like MMTB for multilingual tasks, the standard MTB for English, CMTR for Chinese, and even MTB for code. So a really broad look across tasks and languages.
And what were the main results? What did the report claim?
Well, the report highlights some pretty strong claims. On the MTB multilingual benchmark, the 4B and 8B Qwen3 embedding models apparently achieved state-of-the-art results. They specifically call out the 8B model's score, 70.58, and state it surpasses Gemini embedding on that benchmark.
State-of-the-art is a strong claim. What about other areas?
Similar stories on the English, Chinese, and code benchmarks, reporting strong or superior performance. For instance, the 8B embedding model hit 80.68 on MTB code.
And the re-rankers, how did they perform in the evaluations?
The report indicates they all provided a boost. The 0.6B, 4B, and 8B re-rankers improved results compared to just using the embedding model alone, and also beat baseline re-ranking methods. As you'd expect, the 8B re-ranker performed best among them. The report notes it improved ranking by about 3 points over the smallest 0.6B re-ranker.
And this was tested by retrieving candidates first.
Yes, the evaluation involved first getting the top 100 candidates using their 0.6B embedding model, and then applying the re-ranker.
Now, the report also tried to figure out why these methods worked so well, didn't it? Something about an ablation study.
It did. They conducted ablation studies, basically removing parts of their pipeline to see the impact. The findings presented are pretty clear, that large-scale, weak supervised training stage using the synthetic data was crucial for the embedding model's top performance.
So that massive synthetic data set really mattered. What about the merging?
That too. The report states the model merging stage was also critical for developing strong models. Removing that step apparently led to a noticeable drop in performance in their tests.
So, based on their analysis, both the big synthetic data push at the start and the model merging at the end were key ingredients for the results they reported.
That's the conclusion they draw in the report, yes.
This is all really detailed stuff. One last practical question. Can people actually get their hands on these models? What's the availability?
The report is clear on that.
Yeah.
All the models, Qwen3 Embedding and Qwen3 Reranker, in all three sizes, 0.6B, 4B, and 8B, are publicly available. They're released under the Apache 2.0 license.
Okay, that's great to know. So, wrapping up our deep dive into this technical report, the main takeaway seems to be that this Qwen3 embedding series represents a significant step forward. It builds on the Qwen3 foundation models, uses innovative training like massive synthetic data generation and model merging.
Which, according to the report, leads to state-of-the-art performance on a range of embedding and re-ranking tasks, especially multilingual and code. That really captures the essence of what the report presents.
So a final thought for you, our listener, inspired by this report. Think about this technique they described, using powerful foundation models, not just as the end product, but as tools to generate vast amounts of high-quality, controlled training data. How might that capability, the ability to synthesize targeted data at scale, change how we approach data preparation and model training for future NLP and AI tasks? Something to consider.